So I don't like the argument on the previous slide. So I'm going to give you a different argument for the proof, right? That's a little harder to see. This is much easier to see. Okay. So given that I have two columns, right? Given that I have two columns, each row in the column can be one of these four types. Just assume you have two columns, right? Either both have ones, or one has a 1, the other has a 0, or one has a 0, other has a 1, or both have zeros. Okay. Is that clear? So what is the similarity between C1 and C2? So the intersection will be the number of rows that are of type A, correct? The intersection between the two documents will be the number of rows, or two sets will be the number of rows of type A, right? The union of the two sets will be number of rows of type A, B or C. Correct? So the similarity of C1, C2 is A divided by A plus B plus C. Is it fine? Okay. Now let us say that I have C1, C2 under some random permutation, right? So I start scanning from the top, right? Let us say I encounter a series of rows of type D. That's normally what you would expect, because both C1 and C2 are very sparse columns, right? So you will expect to see a lot of rows of type D, right? You will see a lot of rows of type D. Okay. Let us say you encounter a 1 first. Okay. So if the first row where you encounter a 1 in either of the columns happens to be a type A row, what does it mean? Both will have the same min hash, correct? The first row that I encounter with a 1 in any of the two columns happens to be a type A row, then both of them will have the same min hash, right? So the event that they have the same min hash essentially corresponds to you encountering a type A row first before you encounter B or C, right? So what happens if you encounter a type B row? Then C1 will have that row as the hash value, right? C2 will have some row farther down, right, whenever the first one appears in C2. Right? Likewise, if I encounter a type C row, C2 will have that row as the hash value, and C1 will have a larger hash value somewhere down, right. So both cases it will not have it. Of course, if it is 0, you just keep going, right. So that is not an issue. So it is only when you encounter a B or C, right. Now for them to have the same hash value, you have to select the A before. So the probability that when you are drawing randomly from A, B, C, that the first thing you draw is a A row, right. So that is basically what it is. So the probability that HC1 equal to HC2 is again A by A plus B plus C, correct. So the probability HC1 is equal to HC2 is equal to similarity of C1, C2. That is basically the idea. So now once you think of it this way, then it becomes easier. In fact, the previous slide argument is actually pretty convoluted, so that is the reason we wanted to add this slide, right. So now we know this is true for some arbitrary hash, correct, but then it is still I mean, how would you know that, right? The probability that it is similar for one hash function, probability it is the same for one hash function is the similarity, right. So for me to make a guess as to what the actual similarity is, right, I will do this for several hundred hash functions, right, and look at the fraction of hash functions in which the hash is the same between C1 and C2. So that fraction is going to give me the actual similarity between C1 and C2. Does that make sense, right? So I will do this on multiple hash functions, and the similarity of two signatures is the fraction of the hash functions in which they agree. So already we saw an example where you are creating a signature matrix by doing 3 hash functions, right. So I had something that was 7 rows long, I compressed it into something that is 3 rows long, right. But is that, how good is that, right? So if I look at the actual column similarity, if I compare column 1 and column 3, right. So, what is my similarity? So, 1, 2, 3, right, 3 by 4, right. So, 0.75, and if I look at the two signatures, it is 0.67, not bad, right. And then if I look at 2 and 4, again 3 by 4, if I look at the two columns, they are exactly the same, right. And if you look at columns 1 and 2, the similarity is, in this particular case it turns out to be 0, right. But luckily enough, the signature matrix also gives us 0, right. So, the point here is, okay, pairs of columns which are high similarity, according to comparing directly the columns, also have a high similarity when you are comparing the signatures. Of course, this is just an illustration, right. More often than not, you shouldn't expect this to work because everything is too small, right. I mean, I am just looking at three signatures, I actually only have 7 columns and things like that. So, typically your actual shingle document matrix, right, this matrix on the left will have thousands and thousands of rows depending on the number of shingles that you are looking at, right, and that matrix will typically have hundreds of rows, like a couple of hundreds depending on how many hash functions you want to consider, okay. So, if you have only about a few hundred hash functions versus thousands and thousands of shingles, actually larger number of shingles, you will start getting much better estimates of the similarity between the two columns as opposed to what we have now, okay. Make sense now? Good. So, typically this is essentially how we do it. So, we take the signature as a column vector, right. So, you can convert that into the, because it's got only 100 rows, right. So, I can store the actual index at which the number 1, the first one occurs as a single byte, right, because I have only 100 rows, right. I can represent it as a single byte. So, and if I have 100 such permutations, right, or actually I can yeah, right, the signature of a document is why do I need 100 bytes? Yeah, I need to store 1 for each permutation, right. So, I know I am looking at 100 permutations, and for each permutation I have 1 byte. So, within 100 bytes I can store the document. I do not need the full document representation. In fact, the shingle representation is actually larger than the document representation, right, if you think about it, right. The shingle representation is actually larger than the document representation because I am actually looking at overlapping shingles, right. So, it is much larger than the document representation. I have gone there, but then I finally compressed it down into something that is only 100 bytes long, but I still have retained the property that I can find similar documents, right. But there is a problem with this, right. So, what is the problem? How will I implement permutations? Remember, I have to permute the entire row, that original shingle document matrix, right. So, one column is going to have, couple of million rows depending on how many shingles. If I am using a 9 length shingle, right, the column would have just humongous numbers of rows, right, and I have to permute that column, and I have to do this for all the documents that I have in my collection, okay. So, actually doing the permutation, if I have to take the entire column into my memory and do the permutation, is very hard, right. So, what we do is we actually come up with a small neat implementation trick, right, that allows us to incrementally construct the document signature matrix by reading 1 row at a time of the matrix. I do not have to read the entire column and then do the permutation and then figure out how the signature should be. Basically that's what we did, right? So we wrote down the permutation right next to the permutation matrix, and then try to compute what the signature should be, right? But there's a much more efficient way of doing it, right? No, but swapping is also a problem, right? Because I have to.
You just read your header and then header is position is one, then corresponding rows can be swapped.
No, but then that will still be implementing only one permutation, right? So what we will do now, suppose I want to do 100 permutations, then I have to still read the matrix 100, read the entire data 100 times. So what we will now do is come up with an algorithm that will allow us to do one pass through the data, but compute the entire signature matrix, which is for all the permutations, right? So that's basically what we're trying to do. I mean, the algorithm itself is as with most things, right? So once you realize what is happening, the algorithm itself is simple. Okay, let me walk you through the algorithm first, right? So you start off by let's say that you have two permutations, right? You have H1 and H2 are the two permutations that you want to implement right now. Just for illustration purposes, this can be how many ever you want. You can have 100 such hash functions, right? So and each, because it's a nice prime number, so five rows and all that, we are able to get a nice hash function. It's okay if there are collisions, right? So right now there are no collisions here, but it's okay if you come up with a hash function that's going to have collisions, it's fine, okay? So we have this H1 and H2. You start off by putting in placeholders for all your signature entries, right? So for every document, you can see that, right? So for every document and for every hash function, right here I just made it into sets. I don't have to worry about documents. So for every set and for every hash function, I put in a placeholder, right? Now what I do, right? So I look at each row, right? If that row has a 1 in that column, so that means that that particular shingle is present in the document, right? So for each shingle, each row is a shingle, right? So for each shingle I consider, if that document has that shingle, if the document doesn't have the shingle, then I pass, right? I don't have to do anything. I can just move on to the next column. If the document has the shingle, what I do is I look at, right? So what is the permutation value for the ith hash function, right, in this particular row? So basically, okay, I can go to the next slide. I don't need that, right? So should be S4, right? Right. So these are the ones that have a 1 here, right? So only those signatures can change, right? The rest of it can't change, right? So now what I do is I go and look at where does H1 and H2 send this row to, right? Where do H1 and H2 send this row to? So they take row 0 and then they send it to row 1, okay? So the signature for S1, the hash value for S1 should be at least 1. You get that, right? It can be at most 1, right? So the hash value of S1 can be at most 1, because I know for sure that in row 1 I am going to have a 1 for column S1, right? It can be at most 1. So right now it start off with at most infinity, now it can be at most 1 according to H1, right? And according to H2 again it can be at most 1. So what I will do is, can I search? Okay. So for this S1 again it will become 1. Likewise for S4 the same argument holds, and S2 and S3, because they are zeros, I can't change anything about the hash function. Okay. Is it clear? So I read the first row, I looked at which of the columns had a 1, and then I looked where the hash function sends that 1. Okay, I will now look at that. So it can be at most that value, right? And the current signature seems to be larger than that value, therefore I will change the signature. Okay, now you know where we are going, right? So the next one, next column I am going to look at, so only S3 has a 1, So only S3 can change, right. So now where does H1 send this? To 2, right. So according to hash 1, the signature can be at most 2, it can't be higher than that. Likewise, I look at what hash 2 does, it's 4, right, it can be at most 4, it can't be higher than that. So I basically do that, so I change it to 2 and 4, right. Now I go to row 2, right, oops, okay. I go to row 2, so which are the ones I can change? S2 and S4, right. So let's start with S4 first, right. S4, it says 3 and 2, right, it says 3, if this goes to H1 sends it to 3, right. So I don't change, and H2 sends it to, sorry, here, sorry, it's S4, sorry, that's the 3, so it's 1, I don't change, it sends it to 2, it's 1, so I don't change, right. I know it can't be greater than 1, so I leave S4 as it is, there is no change. And for S2, right, it was originally infinity, so now I can change it to 3 comma 2, that's what this is, right. And then I can finish running this. Row 3 and row 4, only this one changes, right, others can't change anyway. So row 4 only I have to look at S3, and according to hash 1, S3 changes, right. So that's the final hash value, so that's the final signature matrix. We have computed that by one scan through all the rows, right, without explicitly doing the permutation of the rows anywhere, okay. So you understand what the logic is, right. So I start off by saying, okay, all placeholders, and whenever I come to a 1 in the matrix, I look at the corresponding permutation and see where it sends the 1 to. If my current signature is larger than where the 1 is going, then I'll replace the current signature with that location. If the current signature is lesser than where the 1 is going, I'll leave it as it is, right. And one scan through all the rows allows me to compute in parallel all the signatures according to all the hash functions I am considering. So I might have 100 hash functions, I can do all of that in just one scan. And the nice thing is I only need to read it row by row, right. So no point do I need to consume a lot of memory, right. So that's basically where we are. Okay, so now so we have to come up with a way of doing this candidate pair generation, right. So how do we do this, right. So I've used min hash, I've constructed this matrix, right. Now with this matrix, which is basically the signature matrix, right, I am going to start, instead of comparing each of the signature matrix, I still have a large number of comparisons to do, right. I have not reduced the number of documents so far, right. The number of documents is still a million, how many ever columns I had, right. So if I have to do pairwise comparison of these documents, even though I have reduced it to short signatures, right, I still have to do like and choose 2 comparisons across these documents. I still need a way to reduce the number of actual comparisons that I do, right. So we have not yet come there, right. And so how do I do this? So the goal is, now I want to find documents such that their Jaccard similarity is at least some threshold, yes, right. So basically Jaccard similarity, let us say, is 0.8, or the Jaccard distance is at most 0.2, right. So that's basically what I am looking at. So the first simple, let's do the first cut version, right, and then I'll talk about amplifying it. We'll start from that in the next lecture, right. So I'm going to say if x and y, right, are candidate pairs, because these are pairs that I would like to compare the similarity of, and the set of candidate pairs that I'm going to give you with a high probability should contain all pairs whose similarity is greater than 0.8. Okay, so that's what I want, right. If I give you a pair like if I give you a set of candidate pairs, right, with a very high probability they should have all the pairs that are close enough, right, or have a similarity greater than 0.8, right. Ideally, I would like them not to have any pairs whose similarity is lesser than 0.8, right. And what else is ideally do I want? I want to make sure no pair that is has a similarity greater than 0.8 is left out, right. Of course, we do not live in an ideal world, so we are not going to get all these guarantees, right. So, what we are going to do is, so we have the columns of this signature matrix, right. I am going to come up with a new hash function, right, such that if two columns hash to the same bucket, right, two columns hash to the same bucket, right, then with a high probability their similarity is greater than 0.8 or whatever threshold I give. So, I am just using 0.8 as my stand-in for threshold, right. Or the other way of flipping it around, that put it here, if two columns have a similarity greater than 0.8, then with a very high probability they will hash to the same bucket. And then at the end of it I just look into each bucket, all the pairs of elements that have hashed to the same bucket are candidate pairs, right. So, how many ever buckets I have, I will just scan through those and I will get that, right. One sec. Okay. So, the way we are going to do this is the following. So, I am going to take each column, right, I am going to take each column and divide it into m or how many bands, b bands, right. I am going to divide it into b bands and each band is going to have r rows. So, r times b should be the total number of rows that I have, right. So, what determines the total number of rows I have? This is signature matrix. So, what is the number of columns? Number of columns? It is the documents. Number of columns is the number of documents I have. Number of rows is the number of hash functions I have used, right. So, the more hash functions I use, the more rows I have. So, basically since I can choose how many hash functions I want to use, I will choose hash functions such a way that I can write it out into some r times b, okay. So, nicely I can split that and then I get this this kind of a partitioning, right. So, once I have this partition, right, so what I do is I will take two columns, right, and if the two columns are identical, right, I will put them in the same bin, right. If two columns are not, basically each column gives me a bucket, right, each column gives me a bucket, the numbers in the column gives me a bucket. So, I will basically take that bucket, right. If two columns are similar, then they will go into the same bucket. If two columns are dissimilar, they will go into different buckets, okay. Now, what we are going to say is two columns are candidate pairs. I'll just make the statement and we'll stop. We'll come back in the afternoon and look at why the statement is correct. Two columns are candidate pairs if in at least one of the bands, right, those columns are same, they go into the same bucket. If in all the b bands, right, remember each, now instead of a column that is going to have 100 rows, right, I am going to have cut it down into say 5 rows, right? I have 20 bands, each band having 5 rows each, right. So, now just comparing those 5 rows, right, if the two columns are the same, then I will put them in the same bucket. The two columns are different, I will put them in different buckets, just comparing it in the row, right. Now, the statement is if the two columns are not similar in any of the 5 rows, okay, then the probability that the two documents are similar is very, very small, okay. And if the two columns are similar in even one of the b bands, right, one of the 20 bands, if they are similar, then I am going to consider them as a candidate pair that have to be inspected, okay. So, what kind of probability guarantees this gives us, we will look at it after lunch. Okay, so but you understand the statement, right? I've done this, I split it into B bands of R rows each, right? If in each one of those they are different, right, then they are not a candidate pair, right? With a very high probability, they are not likely to be similar. So whatever is your threshold, right? So that's basically what you have to set out, right? So I said similar, but similar in the sense of your threshold argument here, right? So you have your B and R that you can choose. You have the maximum number of rows that you can choose, and you have your B and R that you can choose. And you choose your B and R in such a way that you kind of push the two probabilities as much as possible, right? So the probability that you will accept a pair that is greater than 0.8 similarity, right? You want to keep that probability as high as possible. And the probability that you will accept a pair that has a very low similarity, you want to keep it as low as possible, right? So that means that you have only very few false positive pairs that you have to check, and the biggest challenge here is false negatives. Why? False positives at least you check because you look at the similarity later. False negatives, they are gone, right? You don't look at them again. So usually you are more tolerant of false positives than you are of false negatives. Most applications. In some applications it's okay. You don't really need. For example, people who are similar to you also bought kind of an application, right? So I don't mind if out of 100 people who are similar to me, I get only 80, because that's still useful enough for me to give a recommendation, right? It's okay if I lose 20 people, right? What will be more dangerous in that case is if I get 10 people who are not like me and then start recommending based on their purchase behavior. So in such cases, I might really want to not have any false positives, right? But then I can do a further check and make sure I don't get the false positives. But false negatives are okay in such a case, right? So depending on what application it is. So you can tune your B and R to make sure you get these whatever performance you want, right? Okay. So like I said, we'll just take off from wherever we left off in the morning. So we took the signature matrix. We said we are going to partition it into B bands of R rows each, right? So if you have like 100 hashes, you're going to split it maybe into 20 bands of 5 rows each, or so on and so forth. The idea was that you don't really want to have a single hash to compare, and so we are basically converting each one of these bands into a separate hash function, right? So that we are going to get guarantees of a particular form. Right now I'll just go ahead with this, right, and then we will see what is the general form of the guarantees that we give, okay, as in the second part of the lecture, right? So, and I have to correct something that I said in the morning. So we say that in a band, right, two columns hash to the same bucket only if the columns are exactly similar. Okay. So if there are 5 rows in a band, then in all the 5 rows the 2 columns should match. Okay. And then we say that they have matched and they are hashing into the same bucket. Okay. So that's basically the setup. So we have this here. So I'm going to compare each one of these, and each column, whatever is the numerical combination in the column, is your key to which you are hashing, right? That's a hash value. So for column 1, this is the hash value. We'll put it into a bucket, right? Now if 2 have this 2 columns, for example here column 2 and column 6, right, hash to the same bucket, right? That means that they are probably candidate pairs. So you should take a closer look at them, okay? And if they hash to different buckets, then they are probably different, right? And the thing that we are going to look for is among all of these bands, suppose there are 20 bands, so you can think of it as 20 different hashes that I am doing of the columns, right, of the documents. right? And even if in one of those bands they happen to fall into the same bucket, right, then I am going to consider them as a candidate pair. And only if in all the bands they do not fall into the same bucket, I am going to say they can be safely ignored. Okay. And like I said earlier, there are enough buckets, right, so that two columns that are not identical will not hash to the same bucket. I mean, that is a simplifying assumption that we make, right. So, even if you account for that, it only gives you a small improvement in the accuracy. So, for the analysis purposes, right now we will ignore the fact that two different columns in a band, right. So, that whatever R rows that we are considering, there is a possibility, right, if they are different, also they might hash to the same bucket depending on the hash function you use, right. The simplifying assumption we make it, that does not happen, right. So, they hash into the same bucket only if the two columns are identical, okay. So, that is a simplifying assumption. So, I will not come back to this, right. So, let us talk about this. There are about 100,000 documents and we have about 100 rows, right, and then I am going to assume that there are 20 bands of 5 each. This is the example that we had, right, and then the goal is to find pairs of documents that are at least 0.8 similar, right, or at most at a distance of 0.2 away, okay. So, that is what we are looking at, right. So, remember our assumption, right. So, if we want them to be, if the similarity is greater than 0.8, we want at least in one of those bands they should hash to the same bin, okay. So, what is the probability that they will hash to the same bucket in at least one band, in one band, not at least one band, given a band, what is the probability they will hash to the same bucket? Assuming that these 5 hashes that are there in the band, the 5 permutations that we are using in that band are all chosen independently, that means that each event is independent, right, that hashing to the bucket is independent, therefore, there are 5 such chances that we have, so it is 0.8 power 5. So, that is the probability that C1 and C2, if they have at least 0.8 similarity, the probability that they will hash to the same bucket is 0.8 power 5, okay. Is it fine? Okay. But there is already a small number has become very small now, right, 0.328, right. That is even though the similarity between C1 and C2 is 0.8, the probability that they will hash to the same bucket in one band is 0.328, right. So, what is the probability that they do not hash to the same bucket? It is 1 minus 0.328, right. 0.328 is the probability they will hash to the same bucket. The probability they do not hash to the same bucket is 1 minus 0.328, and we have 20 such buckets. I am sorry, 20 such bands, right. The probability that they will not hash into the same bucket in any of the bands is basically 1 minus 0.328 power 20, because we are assuming all the hash functions have been independently chosen. So, I am treating all events as independent events. So, I can basically say that. Now, so that sounds like a reasonable number, right. So, if I say that I want them to hash into the same bucket in at least one band. Now, across these 20, the probability that they will not hash into the same bucket for all 20 is a very small number. So, with a very high probability, because we have chosen 0.8 as the threshold here, the very high probability, with probability it will hash into the same bucket in at least one band, okay. So, basically that is it comes back to 99.965% of the pairs of truly similar documents we will catch them, okay. There will be a few false negatives, right, and I can see what is the probability of that. So, it is okay, there are a few false negatives. I know I told you that we will completely miss them, we will not get them, right. So, what about false positives? So, we do not really care about false positives because we can filter them out later, but I am just asking, see, The whole goal here is to make sure that we are not comparing n choose 2 pairs, right. We would like to have a small number of pairs that we will anyway end up comparing for actual probability, right, or after actual similarity. So, it is that we should not have too many false positives either, because if you have too many false positives, the entire effort is wasted. So, that is something that you have to think about.
So isn't this 3,000 still large?
Sorry?
Like the false negative was 1 out of 3,000, right? The previous slide. Isn't this?
Oh, it's your slide did change? Okay, good. I wasn't sure whether it changed or not. Okay, I'm go back. Yeah.
The false negative is about 1 out of 3,000. Isn't this large?
False negative is 1 out of 3,000.
Say for some examples, like say some application, like you are trying to identify the fingerprints of some terrorists. So isn't this even missing some 10 out of 30,000?
See, there are a couple of different things here. So, we are talking about looking at all pairs of similar documents. I am not talking about taking a single document and matching it against all documents. So, if you are talking about the terrorist fingerprint and things like that, you will probably be querying a fingerprint against a database, and there are ways in which you can do the matching. I mean, you can try something like a LSH family for fingerprint matching as well, right. But it all depends on the application that you want to look at, right. So, this is, remember I was saying this earlier, if false negatives are absolutely detrimental for your application, then this is not something you want to use. You are happy to look at a lot more false positives, and you do not want to even have such a small fraction of false negatives. And I gave you a lot of examples where false negatives were okay. For example, like I was telling you about recommending walk around, carry around everything. Yeah. So, in such a case, right, where it is okay for me to get even 80% of the true positives, right, even if 20% are negatives, it is okay if I miss them, because all I am really interested in is getting a representative sample of similar users, right. I do not need all the similar users. So, that is why in fact we call these methods near neighbor methods. We do not call them nearest neighbors, because I am not actually giving you any guarantee in any of these methods that the closest neighbor will be retrieved. Right? I mean, it's quite, that's a non-zero probability that the closest neighbor who will be within your threshold, right, might still get missed. Right. So, we do not give you that guarantee. So, you have to look for applications like that where you can use this, right. And yeah, in fingerprints and things like that, yeah, I would not trust on this. Right. You can make that probability even smaller by choosing your R and B differently. You can make that less than 1 by 3,000. It depends on what application you want to use it on, right. So, look at that, we get the true positives are really good, right. So, in this case, so you should go with that, right. So, let us say that C1 and C2 are 30% similar. So, this is the flip side, right. So, we do not want these guys, right. So, we are interested in finding pairs of S that are greater than or equal to 0.8 similarity. Let us say it is 0.3 similar, right. Just, I mean, the same computation. So, I want to look at the probability that they will hash in one band, which is 0.3 power 5, right, and the probability that they will be identical in at least one of the 20 bands is only about 4.74%. That is a small enough number that we have done a lot of filtering now, right. So, yeah, I mean, you would find many documents having low similarity, and you are getting about roughly about 5% of those documents, as opposed to having to look at 100% of those documents earlier if you did not do any filtering. So, that is a significant amount of saving, and we still are able to recover from this false positives, right. So, what we ideally need is something like this, correct. So, the probability of you sharing a bucket should be 1 if you are above the threshold, should be 0 if you are below the threshold, right. So, what does the current setup give us? Let us say you have one band of one row. Basically, what does it mean, one hash, right. just one hash function, right? That's what it means. So that's basically what you get, right? As the probability, as the similarity increases, the probability of sharing a bucket goes up, right? But what we really want is something better, right? We want to get as close as possible to that step function. So what happens is, the way we have done this B bands, R rows per band construction, so this is basically what it is. Suppose the similarity is T, and the probability all rows in the band equal is T power R, right? Yeah, so probability that they don't match in a band is 1 minus T power R, probability that no band is identical is 1 minus T power R power B, probability that at least one band is identical is 1 minus T power R power B. Okay, this is basically what we have, and it turns out that this equation actually looks like a sigmoid function. So we have plotted 1 minus T power R power B as T increases for a fixed B. I think this was the 20 and 5 B and R, right? So for a fixed B and R, we get this, and it turns out that you can solve for this, right? 1 minus T power R power B is equal to T. Okay, solve for that T, right? For all similarities below that T, right, they will be in this region, so likely to be very low. All similarities above T, right, are likely to be increased significantly. The probability is likely to be increased significantly. So this line here, right, where the switch happens from low probability to high probability is roughly equal to 1 by B power 1 by R. We can solve for it exactly, but that's a good enough approximation, right? So depending on what kind of threshold you want, right, you can choose your B and R to approximate the right threshold. So going back, we are working out the same thing now for B equal to 20 and R equal to 5 for different similarity values. This is the probability that they will be declared as a candidate pair, right? There is a probability that at least in one band they will hash to the same bucket. So as you can see that for small values of the probability, right, it's small. For large values of the similarity, the probability is large, right? So somewhere in the middle the transition happens, somewhere between 0.5 and 0.6 the transition happens. So that's a pretty broad band between 0.5 to 0.7 ish, right? The probability is somewhat middling, but after that it just bumps up, right? So something like this. So the blue area is your false negative area, right, and the green area is your false positive area. Okay. And here the similarity threshold is around 0.6, right. So we can tune this M, B and R to get almost all pairs with similar signatures and eliminate most pairs that do not have similar signatures. So what is the difference between step 2 and step 3 here? We are not checking the false positives, false negatives are gone, right. Second step we are checking false positives. Yeah, then third step. Yeah, so basically remember we have translated our document to signatures way back, right. In the very beginning we used shingles and then translated them into signatures. So what I am doing in the third step is ignoring the shingling, going back, retrieving the original documents and actually comparing whether they are same or not, right. So remember that shingling is an imperfect representation of the document, so you lose information. So it's possible that dissimilar documents get the same shingles. So you are basically checking to make sure that doesn't happen, if it is essential for you to make that, okay. So, we already looked at this, so it's a shingling, min hashing and locality sensitive hashing. This is something that's kind of the pipeline for looking at documents, right. So, if you are going to look at directly at sets similarity, you can just skip the shingling part, right. You can directly look at min hashing and locality sensitive hashing part that we did later, right. Okay. So, now I will switch to my actual afternoon presentation. Can I do that?